Dear students, welcome to physics class of PU2. In the previous class, we have discussed about the alternating current chapter. We have discussed about the introduction part, some important terms related with alternating current. What is AC cycle? What is the period of alternating current and the frequency of alternating current, the instantaneous value, peak value, mean value, and the root mean square value of alternating current, and the important term, what is the phase of alternating current and the phase difference. All these points we have covered in the previous class. Now in this class I am going to explain here about the phasors and the analysis of alternating circuits, AC circuits, alternating current circuits. Now, the first point, what is meant by phasors? Phasor is a rotating vector used to represent sinusoidally varying. It is used for what? Sinusoidally varying quantities such as AC current and AC voltage. It is what? It is a rotating vector. It is a rotating vector used to represent sinusoidally varying quantities such as AC voltage and AC current. A phasor rotates in anti-clockwise direction. A phasor rotates in anti-clockwise direction with its period equal to the period of AC quantity. So the period of uh, phasor, that means what? The phasor rotates in anti-clockwise direction and its period is equal to, that means the phasor takes a time period which is equal to what? The time period of alternating current or alternating voltage, and the length of the phasor represents the peak or the amplitude of AC quantity. The length of the phasor represents what? The amplitude or the peak value of the AC voltage or AC current, and its projection on y-axis represents the instantaneous value of AC quantity. Right here, projection. The projection on y-axis. The projection on y-axis represents the instantaneous value of AC quantity. The projection on the y-axis represents what here? The AC value of the instantaneous value of AC quantity. Now let us consider here some examples to illustrate it, right? So here I will let us consider here the first example. So here consider two AC quantities, that means AC voltage and AC current. V is equal to Vm sin omega t and I is equal to Im sin omega t. So in this case what happens? What is the phase difference between these two quantities here? So when V is equal to Vm sin omega t and I is equal to Im sin omega t, that means phase difference pi 2 minus pi 1 omega t minus omega t is equal to 0, right? In this case what happens? The current and voltage are in phase. There is no phase difference between the current and voltage, right? So that phasor diagram is represented in this case here. Like this we have to represent the phasor diagram for when the AC voltage and AC current are in phase. So this length represents what here? The lengths represent the amplitude or the peak value of the AC voltage or AC current, and this projection represents the projection which is taken on the y-axis at any instant of time, that represents the instantaneous value of AC voltage or AC current. Now let us take one more example here. So in this case this phasor diagram is for what? Two AC quantities, V is equal to Vm sin omega t and I is equal to Im sin omega t plus pi by 2, right? I is equal to Im sin omega t plus pi by 2. That means what? Omega t plus pi by 2 minus omega t get cancelled here. Omega t and omega t get cancelled. So the phase difference is what here? Pi by 2. So in this case what happens? The current leads the voltage by pi by 2. Right here the current leads the voltage by an angle pi by 2. So this is the second case here. And again one more example I can give here, that is about when the two AC quantities V is equal to Vm sin omega t and I is equal to Im sin omega t minus pi by 2. Minus pi by 2 means there is a phase difference of pi by 2 between current and voltage. That means the current lags behind the voltage by an angle pi by 2. So this phasor diagram is for what? The when the current lags behind the voltage by an angle pi by 2. So just I am given about the introduction here. Now we have to analyze this analysis of AC circuit. When AC voltage is applied to resistor, when AC voltage is applied to inductor, and when AC voltage is applied to capacitor, then we have to AC voltage is applied to LCR circuit also we have to discuss here. So now let us discuss one by one. When AC voltage is applied to resistor, capacitor and inductor. So in this video class I am going to explain here about the two quantities, that is what the AC voltage applied to resistor and inductor. So the remaining we will discuss it in the next video class. So now let us start about the AC voltage applied to resistor. Okay, now let us explain here about when the AC voltage is applied to a resistor, that is the analysis of AC circuits we are explaining here. When AC voltage is applied to a resistor, so let us consider here a resistor which is connected to a AC source as shown in the figure, and the applied AC voltage is given by V is equal to Vm sin omega t, where V is the instantaneous value of the voltage and Vm is the peak value of the voltage. And let I be the instantaneous current. When the AC voltage is applied to a resistor, the current is flowing through the resistor, through the circuit. Therefore, the I with the instantaneous value of the current flowing through the circuit, then what is the voltage drop across the resistor? That can be written here according to the KVL, that is the Kirchhoff's voltage law or the Kirchhoff's voltage rule. So from the Kirchhoff's voltage rule or the law, what we can write here, the instantaneous value of the current flowing through the circuit. If I is the instantaneous value of current through the circuit, I is the instantaneous value of current through the circuit, then according to the Kirchhoff's voltage rule or the Kirchhoff's voltage law, what we can write here, IB is equal to, that is according to KVL, that is the Kirchhoff's voltage law, what we can write here, that is I into R is equal to V. I into R is equal to V, because of what Kirchhoff's voltage law states, the algebraic sum of the IR products is equal to the what? The algebraic sum of the EMFs present in the various branches of the circuit. That means we have one IR product here. I is the current through the resistor and R is its resistance. So IR product is I into R. One IR product we have here, and the EMF what we have applied here, that is V is equal to Vm sin omega t. Therefore, according to KVL, that is Kirchhoff's voltage law, the algebraic sum of IR products in the various branches of the circuit is equal to the algebraic sum of EMFs, right? Therefore, I into R is equal to V. And the next expression what we can write here, but V is equal to what? I into R is equal to Vm sin omega t. Therefore, I is equal to what? Vm divided by R sin omega t. Therefore, what we can write here, I is equal to I naught sin omega t. So, I is equal to I naught sin omega t. Here we have V is equal to Vm sin omega t. So, this is the Colson's equation number 2. So, from equation number 1 and 2, what we can write here? So, there is a no phase difference between the current and voltage, right? So, this Vm divided by R, what we have written here, this Vm divided by R is equal to I naught, which represents the peak value of current. which represents what? Peak value of current, that is the AC current. Vm divided by R is equal to I naught. It represents what? The peak value of the current. And from equations 1 and 2 we can understood here what? The current through a resistor is in phase with the voltage. The current and voltage are in phase. That means what? V is equal to Vm sin omega t, and I is equal to Im sin omega t. So from these two equations, so this is the phase of AC voltage and this is the phase of AC current. Therefore the phase difference d pi is equal to pi 2 minus pi 1. So omega t minus omega t, this is equal to 0. So that means phase difference is equal to 0. That means what? The current and voltage, the current through the resistor is in phase with the voltage. There is no phase difference between the current and voltage. Now here we can represent the variation of current and voltage with time through the phasor diagram. I will represent here the current and voltage through the phasor diagram. So through this phasor diagram I can explain here how this voltage and current are in phase. So just now what we have discussed here, what is meant by phasor? It is the rotating vector which represents what? The sinusoidally varying quantities such as alternating current and alternating voltage. So here this is the vector here. This is the phasor vector which rotates in an anti-clockwise direction, right? So now this is the phase of the what? The AC voltage and AC current. Omega t represents the phase of the AC voltage and current at any instant of time t, right? So now this length represents what? This is the length of the vector, rotating vector, which represents the peak value of the, this length represents the peak value of the AC current, and this length represents the peak value of the AC current at any instant of time during the rotation. And this total length represents what? This total length represents what? So here what happens? The phase difference between the voltage and current is 0 here. That's why we are getting the two lines. The two lines are coincides here. But in the other cases, when the current and voltage leads or lags, you will get these two lines on in different positions. And this total length represents what? This length represents what? The peak value of the AC voltage, and this length represents the peak value of the AC current. So in this way you have to represent the AC value, in this way you have to represent what? The phasor diagram. And also you can see here the sinusoidally varying AC voltage and AC current, and this is in terms of phasor diagram, right? And this represents the peak value of AC current here, right? This is Im and this is what? Vm, that is the peak value of the voltage and the peak value of the current. So this length represents what here? This length represents, this is the phasor here, right? Again this is the phasor we have to represent, right? Now in this way we have to explain about the phasor diagram. So in this case what happens? When AC voltage is applied to a resistor, the current and the voltage, the AC current and the AC voltage are in phase. That means the phase difference between the current and voltage is equal to 0. Both are along the same line, right? Now let us discuss here the next one, that is when AC voltage is applied to a inductor, and we have to discuss how this current and voltage behaves in case of when AC voltage is applied to inductor. So when AC voltage is applied to an inductor, how this current and voltage behaves. Now let us discuss here. So consider an inductor of inductance L. Consider an inductor of inductance L and which is connected to a AC source as shown in the figure, and the AC voltage applied to the inductor is given by V is equal to Vm sin omega t. So this is the applied AC voltage. V is equal to Vm sin omega t. Call this as equation 1, where V is the instantaneous value of voltage and Vm is the peak value of the voltage. Now at any instant of time, the rate of change of current in the circuit is given by the expression what? Like I is equal to di by dt. So I is equal to di by dt, which represents the rate of change of current. So here di by dt is equal to what? The rate of change of current in the circuit. Then whenever there is a change in the current to an inductor, what happens? There is an EMF is induced in it, right? Whenever there is a change in the current waves, the magnetic flux linked with the inductor changes. Whenever there is a magnetic flux linked with the inductor changes, an EMF is induced in it. Therefore what happens? So the di by dt is the what? The rate of change of current in the circuit. Whenever there is a change in the of the current in the circuit, the EMF is induced in the inductor. Therefore the induced EMF in the inductor is given by E is equal to minus di by dt. So E is equal to what here? The induced EMF, right? E is equal to what? And we have to take the inductance of the inductor, that is equal to minus L into di by dt. So this expression we have studied in the chapter the electromagnetic induction. Therefore the induced EMF in the inductor is given by E is equal to minus di by dt. So this is due to what? There is a change in the current. Because of the change in the current, and EMF is induced in the inductor, and that induced EMF is given by E is equal to minus L into di by dt. So again applying the KVL rule, that is the Kirchhoff's voltage rule, to this circuit, right? So there is no resistor is connected in the circuit, only we have the inductor. So what we can write? According to KVL, that is the Kirchhoff's voltage law, Kirchhoff's voltage rule, what we can write here? V plus E is equal to 0. So we have the applied voltage also we have the induced EMF, right? So according to KVL, the Kirchhoff's voltage rule, what we can write? The sum of air products is equal to the sum of EMF, but we have not connected here resistor, so we have to consider only the EMF, the total algebraic sum of EMF we have to consider. One is the applied one, and another one is induced one. Therefore V plus E is equal to 0. So next what we can write here? V is equal to Vm sin omega t. V is equal to Vm sin omega t, and E is equal to what? Minus L into di by dt. V is equal to Vm sin omega t. Substitute the values of V and E in this equation. So V is equal to Vm sin omega t minus L into di by dt. So just now rearranging the terms, what we can write here? L into di by dt. L into di by dt is equal to Vm sin omega t. Right? L into di by dt is equal to Vm sin omega t. Therefore di is equal to what we can write? Di is equal to Vm divided by L. We want the expression for the current, so that's why we have taken di on the LHS. So Vm divided by L is equal to sin omega t into dt, right? Sin omega t into dt. Now integrating this equation on both sides, integrating this equation on both sides, that is integration of di is equal to, so this Vm and L are constant here, I will take it outside. Therefore integrating sin omega t into dt. So the integration of di is I. Notice the integration of sin omega t. So integration of sin omega t is minus cos omega t divided by omega. That is the reverse process of differentiation. So this is equal to Vm divided by L into minus cos omega t divided by omega. So this is the differentiation of what? The sin the difference integration of sin omega t is minus cos omega t divided by omega. Right? Now what is the next step? What we can write here? So I is equal to Vm divided by L minus cos omega t omega. Now I is equal to Vm divided by omega into L and minus cos omega t. So minus cos omega t, this can be written as what here? I is equal to Vm divided by omega into L. So this can be written as sin omega t minus pi by 2, right? Sin 90 minus theta is what? The cos theta. So just we have interchanged here, so negative sign goes, right? Then I is equal to Vm divided by omega sin omega t minus pi by 2. Therefore I is equal to I naught sin omega t minus pi by 2, right? So this is the expression for the current in when AC voltage is applied to inductor, right? AC voltage, the AC voltage applied to inductor expression is V is equal to Vm sin omega t, and this is what the expression for alternating current, right? AC current which is applied to the inductor. So what is the phase difference you can observe here from the equation 1 and this equation, that is the equation 3. From the equation 1 and 3, what we can observe here? The V is equal to Vm sin omega t and I is equal to I naught sin omega t minus pi by 2, right? Minus pi by 2, what it indicates here then? The current lags behind the voltage. The current lags behind the voltage in case of when AC voltage is applied to inductor by an angle of pi by 2. That means what? Omega t, pi 2 is what? Pi 2 minus pi 1. D pi is equal to pi 2 minus pi 1. So pi 2 is omega t minus pi by 2 and here minus omega t. So these two get cancelled here, right? So again what we can get here? That is angle is pi by 2, right? So angle is pi by 2, omega t minus pi by 2 minus omega t. So angle what we are getting here is that is pi by 2. Therefore, the current lags behind the voltage by an angle of pi by 2, right? Here, current lags behind the voltage. Current lags behind the voltage by an angle pi by 2, right? So now we can draw here the phasor diagram for this. When AC voltage is applied to an inductor, you can draw here the phasor diagram. So this graph shows here what? The phasor diagram for what? When AC voltage is applied to inductor. So here we have got the two expression, that is V is equal to Vm sin omega, and this is the applied voltage, and current through the AC voltage applied to inductor, what we have got here? I is equal to Im sin omega t minus pi by 2, and here Im is equal to what? Vm divided by omega into L. So this Im is equal to Vm divided by omega L. This represents Im is the peak value of the current, and here the phase difference between the voltage and current is pi by 2. That means the current lags behind the voltage by an angle of pi by 2. And here in this relation Im is equal to Vm divided by omega L, the term omega L represents or which plays a role of resistance. What is meant by resistance? Which opposes the current to the circuit, right? Which opposes the flow of current. And in case of inductor, we define here about the inductive reactance. This omega L represents what? The inductive reactance. We call it as what? The inductive reactance. What is meant by inductive reactance? Omega L is the inductive reactance, which is the opposition offered by the inductor to the flow of current. Inductor ಅಲ್ಲಿ resistor ಒಳಗೆ ಏನು ಮಾಡ್ತೀವಿ ನಾವು of resistance R ಅಂತ ಬರುತ್ತೆ, right? Resistor of resistance R which opposes the flow of current. Here, what is meant by inductive reactance? It is the effective opposition offered by the inductor, right? Effective opposition offered by the inductor that can be calculated here by using the formula omega into L, right? Now, how we can write in terms of formula, that is the inductive reactance XL. So XL, X with suffix L, it is denoted by this X with suffix L represent the inductive reactance, and XL is equal to omega into L. And you know that omega is equal to 2 pi, omega is equal to 2 pi nu, or we can write F, but again we have L here, right? 2 pi nu into L, where nu is the frequency of AC current and L is the inductor of inductance L. Therefore, the inductive reactance is directly proportional to what? The inductor of inductance L. So, and also it is defined as what? XL is equal to Vm divided by Im, or also it is defined as Vrms divided by Irms. It is the ratio of RMS value of voltage to the RMS value of AC current. And we can represent this, and the SI unit of the inductive reactance, the SI unit of the inductive reactance is also ohm. You know that the SI unit of the resistance is ohm, and here the SI unit of the inductive reactance is also ohm. SI unit is ohm. Ohm is the SI unit of inductive reactance, and the variation of the inductive reactance with the frequency we can show here, because the inductive reactance is directly proportional to the frequency, right? So the graphical representation of the inductive reactance versus the frequency we can represent. This is a linear relation, right? As the frequency increases, the inductive reactance also increases, right? And for DC circuit, there is no inductive reactance, because XL is equal to 0 in case of what? The DC current, right? For DC current, XL is equal to 0. So this is the important point what we have discussed here is about when AC voltage is applied to resistor and when AC voltage is applied to inductor. There is no phase difference between AC voltage and current in case of when AC voltage is applied to resistor, but in case of when AC voltage is applied to inductor, there is a phase difference of pi by 2. There is a phase difference of pi by 2, that means current lags behind the voltage by an angle of pi by 2. And this Im is equal to Vm divided by omega L. This is in terms of Ohm's law, we can write V divided by R. So this omega into L plays a role of resistance in inductor, and this XL is equal to omega into L. Omega is equal to 2 pi mu L, right? And also XL is equal to Vm divided by Im. In terms of the peak value of current, inductive reactance is defined as the ratio of peak value of voltage to the peak value of current. And in terms of RMS value of voltage and RMS value of current, inductive reactance is equal to Vrms divided by RMS, and the SI unit of the inductive reactance is ohm. The SI unit of inductive reactance is ohm, right? So finally, inductive reactance is nothing but which is the opposition, the effective opposition offered by the current to the flow of AC current. And this is about the today's class what we have discussed. In the next video class, we will discuss about what? The AC voltage applied to the capacitor. AC voltage is applied to capacitor, and AC voltage is applied to a series combination of inductor, capacitor and resistor. Okay, thank you students. We will continue in the next class.